Let's now make things a little more complicated by adding damping to our simple harmonic motion. As before, we've got a spring providing a restoring force through Hooke's law, negative kx. But now the mass we can imagine is moving through some sort of a fluid that sucks energy out of the motion and eventually causes the mass to come to rest. We'll model this damping force as negative r x dot. So it's a force in the opposite direction to the velocity x dot and some constant r, which depends on how thick the fluid is, so it's a damping constant. An example might be a piston with some fluid or a pendulum moving in air. So if we add up the forces, as before, we've got Hooke's law giving the restoring force. We've now got a viscous force, negative r x dot. And some of these forces must be equal to mass times acceleration. So mass times acceleration must be equal to negative kx minus r x dot. And this is an equation of motion. Rearranging a little bit, we can write it as x double dot plus r on m x dot plus k on m times x is equal to 0. So this is an equation of motion for a damped oscillator. Some maths terms you may have heard elsewhere that are useful here, just to put things in context if you've heard these terms before. Damped harmonic motion, this is the equation here, is a homogeneous differential equation. That means each term in the equation has x or its derivative. It's linear, so there are no terms that depend on x in any nonlinear way. There's no x squared or x dot squared. That's a linear equation. It's second order. That is, the highest derivative is order 2, x double dot. If we have functions x1, x2 of time that are solutions of the linear homogeneous differential equation, then some linear combination of x1, x2 is also a solution for all constants ci. The values of ci must be fixed using some initial conditions. An nth order linear homogeneous equation has n arbitrary constants in its general solution. That is, here we have the second derivative as the maximum derivative, so we have two solutions that we add together in some linear combination to fit initial conditions. If we had an nth derivative, then we would need n solutions that we sum together in a linear combination. Let's now rewrite our equation of motion in this form. This is a very general second order differential equation where we have some rate gamma and some rate omega naught. And for the case of a spring and a mass, gamma is a damping rate with units of seconds to the minus 1, and this is given by r on m. And omega naught is the resonant frequency for the undamped system of omega naught squared is equal to k on m. So gamma and omega naught are now things that both have units of seconds to the minus 1. And if our system were different and we weren't dealing with a mass and a spring, we might be having an electric circuit or something else, then we can fit it to this equation just by having different values of the damping rate and the resonant frequency in terms of different physical parameters that now have to do with electrical circuits or whatever it is. So solving this equation keeps things fairly general. We'll try a solution of the form x equal e to the alpha t. That means x dot is alpha e to the alpha t, and x double dot is equal to alpha squared e to the alpha t. And we'll substitute x dot, and x double dot into this equation and try and find a value of alpha that solves our equation. So doing this, we find that all this must be equal to 0, and we can take out a factor of e to the alpha times t. So we take out that factor and we can multiply through by, or divide through by e to the alpha t, which leaves us with this quadratic equation for alpha. So we can solve for alpha, and we get alpha is equal to negative gamma on 2 plus minus the square root gamma on 2 all squared minus omega naught squared. Or in other words, we have two values for alpha, alpha 1 with a plus here and alpha 2 with a minus sign here. And the general solution of our differential equation is thus some constant c1 e to the alpha 1 times t plus c2 e to the alpha 2 times t. Now looking at this more closely, we can identify three cases. One is where gamma on 2 is greater than omega naught. So gamma on 2 is greater than omega naught means everything under the square root here must be positive. That means alpha 1 and alpha 2 are both real negative numbers. And this is called the overdamped case. Case 2 is where gamma on 2 is less than omega naught, which means everything under the square root here and here must be negative. So we're going to get a complex number for alpha 1 and alpha 2. And this is called the underdamped situation. Case 3 is the sort of pathological case where gamma on 2 is equal to omega naught, which means that alpha 1 is equal to alpha 2. This is called critically damped, and we need to follow a different strategy to find a complete solution to this third scenario.